Hi everyone, in this video we are going to discuss this example. What we have a matrix space XD. X is a finite set having finite number of elements and D is any matrix. What we have to prove? We have to prove that every Cauchy sequence is eventually constant sequence, okay, and after that we have to prove XD is complete. So let us start to discuss how to prove every Cauchy sequence is eventually constant. Let us try to understand what is eventually constant sequence. We are familiar with a constant sequence, right? Constant sequence means all terms are same. Agree? Eventually constant, that means first few terms can be different, but after a fixed term you will have all same terms. Just like this, 2, 3, minus 9, 7, 8, 8, 8, 8 and so on. All remaining terms will be 8. So first few terms are different and after that we will have a same term. So we call it as a eventually constant sequence, and here we have to prove every Cauchy sequence in XD is eventually constant sequence. Let us start to prove. What will I do? I will start with a given information, okay. What is the information we have? X is a finite set. Let me mention, we have X is finite. X is finite set, that means having finite number of elements. We are assuming it has n number of elements and having n number of elements, n number of distinct elements, okay. I should mention n number of distinct elements. So so that means let us assume those elements are x1, x2, x3 and so on. The last element is xn, right? Let me draw the diagram so we can easily understand. Suppose this is x1, this is x2, this is x3, x4, x5, x6, like that, okay. So having n number of elements. Now what will I do? Let I am going to define a small r, okay. It is in this way. It is minimum of d of xi xj, where I and j running from 1 to n and I is not equal to j, okay. What we are doing? We are finding the distance between any two distinct elements, just like distance between x5 and x3, distance between x1 and x6, distance between x4 and x3, distance between x2 and x3. All possible distances we will find, just elements must be distinct, okay. If you take same elements you will get distance 0, but we are considering all distinct elements. And what will be the least distance? What will be the minimum distance? That is nothing but r. So in that particular diagram you can easily see this is a minimum distance as compared to the other distances. So that will be my r, right? Let us continue. So yes, in this way I have chosen my r. Obviously it is greater than 0, okay, greater than 0, strictly greater than 0. And yes, in this way I have defined r. So what we have to prove? We have to prove that every Cauchy sequence is eventually constant. So let us start with one Cauchy sequence and we will prove it is eventually constant. Let xn be any Cauchy sequence in matrix space XD. I have taken any Cauchy sequence. We are familiar with the definition of Cauchy sequence. For given epsilon greater than 0, there exists capital N belongs to set of natural number and so and so. So that means we start with epsilon, which is a positive real number. So let us start. Here r is also positive. Let me mention clearly, r is also greater than 0. So I will choose my epsilon is this r, okay. So therefore for epsilon, I am choosing epsilon as r. It is also positive, so our epsilon is also positive. There exists some fixed natural number n0 such that d of xn xm less than epsilon for all nm greater than or equal to n0. So by definition of Cauchy sequence I got this one. Now what will I do? I will fix that m, okay. So I am taking a particular value of m, which is n0. So let me mention in particular particular d of xn x n naught less than epsilon for all n greater than or equal to n naught. I have fixed my m, which is n naught, so that's why I got this one, right? Epsilon, but what is value of epsilon? R. Let me put there. So therefore d of xn x naught less than r for all n greater than or equal to n naught, right? Distance is less than r, but see, r is a minimum distance. R is the smallest positive smallest distance, and here we are getting distance less than r. So that means distance must be 0. In this diagram also you can see this is a minimum distance, and here we are saying distance between these 2 points is less than that minimum distance. That means obviously the distance must be 0. So let me mention here. So therefore that distance must be 0. D of xn x naught is equal to 0 for all n greater than or equal to n naught, right? So tell me, when we get the distance 0, if both points are same, then we get distance 0. That means both points are same. D of that means xn is equal to x naught for all n greater than or equal to n naught. Getting the point? Xn is equal to x naught for all n. That means the sequence will be like this: x1, x2 and so on, x n naught minus 1, okay. Next x n naught. Here we are saying if n is greater than n naught, the term is a x naught, that x naught. So that means here at xn is also x naught, here xn I should write, x naught, x naught, x naught and so on. So this is definition of eventually constant sequence. So that's why we say xn is eventually constant. So here we got the definition of eventually constant sequence. So therefore I can declare, therefore sequence xn is eventually constant, okay. So in this way we proved if you take any Cauchy sequence in xt, it is eventually constant in xd. So the first half is done, that every Cauchy sequence is eventually constant in xd. Now we have to prove the second half. We have to prove that xd is a complete matrix space. Just make a screenshot of it, then we will go further. So now to prove that xd is complete, just tell me when we say the matrix space is complete. Okay, tell me when we say matrix space is complete. If every Cauchy sequence is convergent, then we say the matrix space is complete. That means here we have to take any arbitrary Cauchy sequence and we have to prove that it is convergent. Okay, so let us start to do. So let an be any Cauchy sequence. Okay, I am taking any Cauchy sequence in xd. But just now we proved every Cauchy sequence is eventually constant. So this is Cauchy sequence, that means this is also eventually constant. Implies n is eventually constant sequence. I am mentioning the reason. The reason is every Cauchy sequence is eventually constant in xd. Okay, just now we have proved, so I am using that thing here. Okay, it is eventually constant. Eventually constant means what? First few terms are different and after a fixed term you are having all same terms. Okay, so therefore by definition of eventually constant sequence, we will find some k such that n is equal to a for all n greater than or equal to k. That means if you go further, okay, if you go above the k, you will get all same terms and I am calling them as a. That means sequence will be like this, that a1, a2 and so on, ak minus 1, and after that from k we will have a like this. Okay, such type of sequence we have. What we have to prove? We have to prove that it is convergent, right? Since we have to prove it is a complete matrix space, we started with a Cauchy sequence. So finally we have to prove it is convergent, then we can declare it is complete. Okay. So now what will I do? I will prove that sequence n converges to a. Now we will prove n converges to a in xd. Okay. So, we are familiar with the definition of convergent sequence. For given epsilon greater than 0, there exists a fixed natural number, right? So, let us take one epsilon. Let epsilon greater than 0 be given. I am taking any arbitrary epsilon, C, and I am going to consider d of n comma a. This is equal to, as you can see here, n is equal to a for all n greater than or equal to k. So, I can write this is equal to d of a comma a for all n greater than or equal to k. Since n is equal to a with this condition, so I have added this condition here. So, that is why I could replace n by a. What is the distance between a and a? Points are same, distance is 0, right? But epsilon is greater than 0, so that is why 0 less than epsilon, that is, let us conclude d of n comma a, we got it is less than epsilon with this condition. See, this is definition of convergent sequence. Therefore, n converges to a in xd. So, in this way we proved any arbitrary Cauchy sequence is convergent, right? So, therefore, every Cauchy sequence is convergent in xd. So, this is definition of complete metric space. Therefore, xd is complete, right? So, in this way we have completed this proof. Just make a screenshot of it, then we will stop. Thank you. See you.